this video, we'll see memory layout in C programming and we'll try to understand how virtual memory space is allocated to different sections. Here code segment is at bottom. Next, initialized data restored. Then uninitialized data restored. Code segment and initialized data segment are initialized with memory at compile time itself. Heap and stack segment are allocated for a program at runtime and it grows in opposite direction. Topmost segment is for command line argument and environment variables. As per its name, we can understand that it is used for command line arguments. Now we'll see one by one for each segment. Code segment. This is the bottommost segment. This is also called take segment. It consists of executable program instructions. This code segment is kept far away from runtime allocatable segments, heap and stack. So overflow of runtime memory allocation will not impact code segment. This is read-only segment which will avoid accidental modification. This segment is shareable to compiler, text editor, shell and so on. So only a single copy is needed in memory. Initialized data segment. It is simply known as data segment. It consists of global or static data initialized with non-zero values. Uninitialized data segment. It is also known as BSS, block started by symbols. It consists of global or static data either uninitialized or initialized with zero value. Data in this segment is initialized by kernel to zero value before program execution. Let's understand with an example about initialized or uninitialized data segment. Int global data 1 equals to 4. This global variable is initialized with non-zero value, so it will be stored in initialized data segment. Int global data 2 equals to 0. This global variable is initialized to 0, so it will be stored in BSS. Int global data 3. This global variable is uninitialized, so it will be stored in BSS. Static int local data 1 equals to 4. This local variable with a static keyword and initialized to non-zero value, so it will be stored in data segment. Static int local data 2 equals to 0. This local variable with a static keyword is initialized to 0, so it will be stored in BSS. Static int local data 3. This local variable with a static keyword is uninitialized, so it will be stored in BSS. You can check the memory allocation detail for an executable file with size command. Next segment is heap. It is allocated at runtime. This memory segment is used for dynamic memory allocation with malloc, realloc and calloc. It goes towards stack. It is located at higher part of memory. This segment is also allocated at runtime. It contains program stack. A program stack contains all function calls whose base is main, as the main function called first. So the stack frame will be allocated first for the main. A stack frame contains automatic variables, means local variables, input parameters, return address of calling function, means address of next instruction in calling function, so that the program execution will resume in calling function after the completion of execution in called function. A stack works with LIFO structure, last in first out. A stack pointer always points to the top of the stack. Lastly entered stack frame will be popped out first. The problem may occur with a stack and heap as they are allocated at runtime and it grows in opposite direction, which may lead collision for both segments. Now we'll understand in detail about stack and heap issues. First about heap issues. As we understood that heap is allocated at runtime with dynamic memory allocation using malloc, realloc and calloc. It is programmer responsibility to free the allocated memory using free API. If programmer doesn't free the memory after use, it will be a situation of memory leak. Means memory will be still allocated, which is not going to be used ever. It will reduce the available memory, which may degrade the system performance. Next, we'll understand the issue with a stack. As we know that a stack contains all function calls, means all stack frames. Let's take an example of recursive function. Here we are having main, where we are calculating factorial of 4. So one stack frame will be created for main function. Next, one more stack will be created for the factorial API. This factorial API calls itself recursively, and it is having base condition val equals to 0, where this recursive calling will end up. Here main calls factorial of 4, so a stack frame will be created. Factorial 4 calls again factorial 3, so another stack frame will be created. Factorial 3 calls again factorial 2, so another stack frame will be created. Factorial 2 calls again factorial 1, so another stack frame will be created. Factorial 1 calls again factorial 0, so another stack frame will be created. Here a stack frame will be created one after the another recursively, and it will end at base condition. The issue arises when programmer put the base condition wrongly or forget to put base condition. This will lead the recursive call to go infinite, and this will create a situation of stack overflow.